Hello, welcome everyone. I'm Sherlock. I'm from PyTorch compiler team of Meta. So the work I'm about to present is a joint work between PyTorch compiler team and ExecuTorch. And the topic today is beyond TorchScript and the future of Pythonless inference in PyTorch. So I guess today we have a full room of people who actually care about the fate of TorchScript. And today I'm going to share a few news about it. First of all, let's revisit why we have TorchScript. All right, let's first talk about the purpose of Pythonless inference. PyTorch is all good, and everything is in Python. It's like why we try that hard to get out of Python and try to do inference. There must be some constraint behind it that you have to ditch the Python for good reasons. And we know that this is commonly the practice in productions. So when you look at this few scenarios, especially the edge or the metaverse or some mission critical systems, typically they requires low latency and tight memory budget. And this is why you need to get out of Python, get rid of all the Python overhead. And typically what you have is a C++-like runtime environment. So here's the reason why people really like Pythonless inference. So first of all, it's for much lower latency. In the mission-critical systems, every microsecond counts. For example, self-driving car, you want it to be a real-time system. You cannot imagine running Python in it. And also, Python is an interpreter-based language, and the interpreter layer just adds another milliseconds, microseconds of the overhead to achieve this kind of deterministic run for real-time speed. Usually, people would vote for C or C++-based implementation. The second reason is resource constraint. For example, the edge device and embedded system are typically limited by the amount of memory and power you can use. So Python requires a bulky interpreter. Usually, it's not the right fit. So without Python, such no Python runtime are typically lightweighted, optimized for memory and power that is more suited for such scenarios. The last reason why people opt for Pythonless inference is it makes the deployment cycle a bit easier. So we want to deploy the entire Python environment. We simply just want to export a model into some kind of compressed format that is portable, and then you can ship it into multiple environments. So the rule of thumb here is that use Python for the heavy lifting training phase, where you can, you want the flexibility of the eager experience. But when it gets to production grade inference, people opt for C or C++ inference engine for a high stake, low resource demand on the edge. So let's take a bit look back into the history and revisit our old pal, TorchScript. TorchScript is the core technology that enabled PyTorch model to run independent of Python. Historically, it's the bridge from a research model to a production system. So to create a TorchScript model, there's commonly two ways. You can either git.script it, which is doing Python DSL parsing to create a static graph, or you can do a git.trace, which is tracing tensor operation that's happening in the dispatcher level. But at the end of the day, you get a graph in TorchScript IR, and then you can do all kinds of optimization on it, try to compile it, and eventually package it into some kind of format. Typically, it's .pt file. And then the result thing is then deployed to a runtime. In this case, it could be TorchScript interpreter or static runtime. So this is the typical workflow in the historic TorchScript stack. And over the years, people have deployed TorchScript in their systems, and we have run into various kind of problems. We consider TorchScript kind of our first generation of a like torch capturing and compiler technology. Over years, we have developed multiple iterations. So for example, we have experimented with symbolic trace, and more recently with PT2-based like torch export graph capture. So we're going to revisit the problems we had with TorchScript, and we will learn that like from this problem, we made new design decisions in our new systems. Number one, the front end. As I have mentioned, there are two front ends. There's a TorchScript front end, a TorchScript front end, which is very picky about Python syntax. Like if you have worked with TorchScript, you know that you need to write your model in a particular way in order to make the scripter happy. There are a bunch of Python features that you simply cannot use because TorchScript doesn't support it. Because of its nature, it has uneven coverage on Python features. Some are supported, some are not. So there are very common requests about why don't you support this Python feature like named argument, because that's not implemented, so it's not supported. It adds a bunch of complexity to the PyTorch code base. So those are the G.script problems. On the other hand, you can have a G.trace, which is a tracing-based tensor operation system. The problem is that it's unsound. What you get in the end is a straight line graph. Even if there's some like if-else branch in your code, you doesn't see that. You just faithfully record what you have encountered during this particular instance of trace. And another problem is like it lost the Python structure because the tracing is happening inside CPP dispatcher, and you have no knowledge about what's happening in the outside world. So it's very hard to link the Python original Python user code, Python structure in user code back to the TorchScript graph. Okay, then moving on to the next set of problems, that is people want to do optimization when you have such a graph. However, tensors in TorchScript IR doesn't necessarily contain all the metadata. There's no guarantee that the tensor has the information about like shape, d-type, stroid, and layout, which are very critical for you to later do optimization on it. If you want to do any kind of fusion or memory planning, usually you are relying on tensor metadata to do a good job. So essentially, like people apply workaround by running additional passes to populate those, but those are not very reliable. Yeah, that's a limitation. Another problem is TorchScript IR expose all PyTorch apps to you. So as of today, it has over 2,000 apps. If you are a backend that tries to integrate against TorchScript IR, you have a very large surface to work with. Yeah, often this is prohibiting like backends from implementing a reasonably good backend for a large set of model coverage if you are talking TorchScript IR. Now let's look at the problem of the TorchScript IR itself. Let's just look at this example here. This is a very like artificial example, which is a function that takes in a dictionary and a string and a tensor as input. And in the function body, you do some like dictionary lookup and string manipulations. The good thing about G.script is that if you script it, all of these Python-like operations are actually included in the IR, which is a bit crazy, but like it's there. You can see that there is like concat for the string, there is like dictionary lookup or dictionary set. So typically, an ML compiler only cares about two things, right? It cares about tensor operations, it cares about shape computation. So in PT2 term, they are cement. These are the only two constructs that a typical ML compiler cares. But in the TorchScript IR, we are putting a lot of non-tensor operation into the IR, and those are hard to work with from a compiler's point of view. So this introduced this unnecessary dynamism into the IR. Usually, compiler would ignore it or try to write a path to get rid of it. But at the end of the day, TorchScript IR is not the right IR. That is, if you are trying to build a backend or compiler against it. Another word about control flow. People love control flow. One thing that people really love about TorchScript scripting is it automatically captures the control flow, like if-else branch or while loop for you. This is good in the sense it captures all the if-else condition automatically for you. However, it also captures a lot of things that doesn't necessarily need to be dynamic. So everything, regardless whether you intend it to be dynamic or not, they are faithfully captured in the graph. As you can see in the example here, this simple program turns into this complicated IR, which has the prim.if in your resulting graph. And if you're compiler people, you know that branching is a poison for compilers because you don't see the global picture. Things are localized. You can only optimize for this small if-else branch of the graph, and it prevents global optimization such as fusion and reordering. So essentially, it's good, but it's too much. It introduces a bunch of unnecessary dynamism, which make it hard for compiler to compile. And then there's a problem of compatibility. There are multiple fold of compatibility problems. The compatibility problem, Python itself and PyTorch itself is a constantly evolving instance. So there are compatibility issues between TorchScript and modern version of the Python, and then not to even mention the new feature that is happening in PyTorch 2. So it's simply not compatible with, it's the legacy TorchScript is not able to keep up with the new developments. And then also there's this offset problems. Because of this 2,000 plus offs that are exposed in the TorchScript IR, not all of the offs are guaranteed to be BC. There are cases where, when you have operator definition BC breakage, your TorchScript graph becomes invalid, and when you run it, it just fails. Yeah. So, and finally, when you have a graph and you do optimization, okay, you reach the final runtime stage. What kind of runtime you can actually build with such a graph? The best you can do is interpreter. Yeah. So you just run the graph node by node after applying some optimizations. And because and then at the end of the day, you're gonna rely on PyTorch dispatcher to run the node for it. So dispatching overhead is kind of large, yeah, it's not very nice. So at the end of the day, we come to a conclusion that we actually have attempted to build multiple versions of compiler based on TorchScript IR, and we are not able to shape a very good ahead-of-time compiler based on TorchScript IR. And we came to a realization that this is very hard to fix incrementally. Like I said, it's futile to chase the evolvement of Python and PyTorch. It's a dynamic language, and you're trying to capture everything in a static graph with a limited set of IR definitions. It's a losing battle. Second issue is that it's coming from its fundamental design of TorchScript. So, for example, it tries to capture everything. Every Python language feature are somehow representable in a TorchScript IR. So any BC breaking change of PyTorch or Python will cause the whole IR to crumble, right? So it's not very BC compatible. And finally, we have To reach a real production-grade runtime efficient, we just have to rewrite from scratch. So the overhead we have just discussed is not like something we can patch and to be fixed. So for all this, we need to abort the legacy interpreter and build a new foundation that is free of this design choices that we made in the beginning. So starting fresh is the only way to deliver a good and speedy stack that user wants. So we come to the announcement today. So because of all the limitations and problems that I have stated above, we have decided to deprecate TorchScript, starting from PyTorch 2.9 release. But don't panic. This is a controlled sunset. I want to be clear that there's no intermediate implication of TorchScript deprecation today. So everything is a controlled deprecation instead of an abrupt shutdown. First of all the existing TorchScript builds will still be maintained for stabilities. However, it's going to be feature frozen. We are not going to be developing any new features on top of TorchScript. There will be bug fixes, but it will only be bug fixes for security issues. Right? And we are starting this hard pivot by deleting the documentations from our PyTorch 2.9 docs. So if you go to the documentation page, you won't find TorchScript. You can go back to the older versions, but that's our way to signal to the world we do not recommend new users to use TorchScript. Finally, I have a clear end date. So the code deletions for plan of records is going to be 4 more cycles, targeting version 2.14. This gives us the community and industry plenty of time to move and transition. All right. Now we have talked about history. Let's look ahead and see what's beyond TorchScript. So over the past few years, you have seen TorchScript, you have seen PT2, and we have been actively working on the successor of TorchScript, that is ExecuTorch. So it was built on top of the latest technologies that we create, and it's stemmed from Torch Compile and Torch Export stacks. So you might have heard it from the previous talk that Morgan gave. ExecuTorch has reached its GA and 1.0 today. So we encourage you to explore ExecuTorch as a solution, a replacement solution for TorchScript. So a few quick overview. TorchScript follows a very similar stack as the ExecuTorch follows a similar stack as TorchScript. So in the sense that you have an eager array module, you do graph capture. The new graph captured is Torch Export. What you get is an FX18 graph. And then you can do optimization and ExecuTorch lowering to optimize it. And finally, it becomes a binary that is deployable. And then you deploy it. You run the actual lowered artifacts in ExecuTorch runtime in your favorite mobile, embedded, or desktop environment. So why it's better than TorchScript? First of all, the graph capture frontend is now different. So we have released Torch.export about 2 to 3 years ago. So we have been using it extensively internally. So just to quickly recap, I think most of people is already familiar with this. It's a tracing-based graph capture that doesn't produce too much random Python syntax. It has a much fewer gaps with the existing Python features. Also, because of Dynamo, it has a soundness guarantees that the dynamic shape that you capture during the tracing correctly populated. All the tensor in the FX18 graph has metadata information attached to it so that your backend or your compiler can reasonably optimize for it. Also, it's compatible with our latest advancement in PT2. So it's up-to-date support for new features like tensor subclass. You will never be able to TorchScript a tensor subclass, but you are able to export it in Torch export. Yeah. And then there's also a lot of interest in like implementing your own kernel in Triton. Same here. You cannot do this in TorchScript. TorchScript doesn't understand Triton, but export understands Triton. So you are able to capture the Triton kernel. Just a few words about export IR. So like I mentioned, A10FX graph has all the nodes metadata populated. So it gives you a rich set of like tensor metadata, allows you to do further optimization on it. And also it's the edge dialect will provide even stronger guarantee on the operator set that could show up in the resulting FX graph. So what you're gonna get is a functionalized set of operators that we have handpicked and maintained and give them BC guaranteed. So this is what we call edge dialect. If you need further optimizations on your own dialect, you can also do customization by adjusting the decomposition, and then you will have your own offsets. There's a long list of optimization that we have put into ExecuTorch stacks, such as the set of our quantization and implemented memory planning. And look at this long list of like delegation backend that ExecuTorch has integrated with. I'm not gonna go through all of them, but like we have closely working with all the hardware vendors to port their backends into ExecuTorch stacks. Finally, I just want to say one thing about the ExecuTorch runtime. It has a low overhead, and it's very small. It's just like 50 kilobytes. And under here is an efficient C++ implementations. It supports a wide range of architecture like Linux, all the common ones. But specifically, like to mention the iOS and Android targeting the mobiles, and there is an embedded device. Now, just to give you a few caveats about like this is work in progress. So ExecuTorch currently mostly targets mobile, edge, and desktop device only. All right. So the control flow can be captured with Torch export, but you have to do manual rewrite. You have to rewrite it into a torch.count kind of like higher order ops. If you understand, if you know what torchbind is, torchbind is not going to be supported. If you don't understand what torchbind is, don't worry about it. Like it's legacy stuff. You don't want to know about it. Finally, like the NVIDIA GPU support and meta support is experimental. We are bringing AOT inductor into ExecuTorch stack. We are able to compile a model into Triton kernels by inductor and deploy it with ExecuTorch. Okay, a few words about next steps. We're going to continue to support more models on the desktop. Of course, like the front end is going to continue to evolve to keep up with the new Python and PyTorch features. Because like this is all PT2 native, it's easier to do this. We are going to like mature AOT inductor for better GPU support. There are two examples that we have released today, Voxar and Gemma 3. Like, if you're interested, you can go to the link to look for more examples. These are generative models, by the way, and they are multi-model. They are not just LLM. This shows case that like how easy it is to take a multi-modality, like generative model, going through export, and then deploy it in ExecuTorch stack. And this has been a lot of adoption. You have seen this in the keynote slides, so I'm not going to repeat myself, but it's widely used and has been adopted by ecosystem across multiple parties. Finally, I encourage you to try out the new ExecuTorch stack. There are tutorials and examples, and I will let people take pictures, and there are like Discord that we have developers there to interact with you. So if you need more like real-time interactions, go to this Discord, and also we are always available in GitHub issues. So that's all for today. Thank you very much. And I will have 30 seconds to take questions. Yeah. Yep.
What happens to libtorch serialization operations in C++?
Can you say it louder?
Libtorch C++ serialization, loading and saving.
libtorch serialization, which one are you referring to?
You use, I believe, the torch JIT operations for serialization of C++ modules.
Are you talking about like custom class? Okay, that's the torch support. So this is a custom C++ class which you can define your own serialization and deserializations. Right, so this is another name is in TorchScript. That's the TorchScript app. So currently it's graph capturable by Torch export. However, the ExecuTorch stack hasn't implemented support for that. Yeah. Yeah, no questions?
So if we want to use ExecuTorch for model study, cover use cases, what is missing? If we want to use ExecuTorch for model serving, server use cases, what would be missing?
Serverless deployments?
Model serving use cases, what would be missing?
Yeah, so is it like on mobile edge scenario or?
No, like data center.
Sorry, I'm.
Servers.
Oh, servers like deployments. I think the main problem is that like our CUDA support is still work in progress. So on server, you need perf, you need CUDA, you need AOT inductor. But AOT inductor is still experimental. I think currently our major focus is still on desktop, but less of on a server. Yeah.
Thank you.
Cool. Sorry, I don't have time for another question, but we can talk offline. Thank you.